All right, let's take a look at section 14.4, which covers tangent planes. So, a couple of learning objectives this time. Compute a tangent plane to a surface, which is the first thing we're going to look at here in a moment. And then also determining error using differentials, which is going to be an application of linearization, which is a Calc 1 topic that we're going to revisit in 3-space. But let's start off with the definition of a tangent plane. What we want to do with our tangent plane is sort of extend the idea of a tangent line from Calc 1 that we had in just a plane. We can look at some curve and find its tangent line, and extend that out to a tangent plane that exists in 3-space. So our definition for the tangent plane to some surface at some point is going to be a plane that contains all of the tangent lines to that point. Since this is now a two-dimensional surface, some curved two-dimensional surface that exists in 3-space, I can find tangent lines in just about any direction I want, which means that there are an infinite number of tangent lines I could collect. But if we want to find the plane that contains all of our tangent lines, we really only need to find 2 of our tangent lines, since that should be enough to define the plane. And then, well, the plane will collect all the rest. So what we'll say is that if f has continuous partial derivatives, then an equation for the tangent plane at the point x0, y0, z0 is the thing listed out below. Z minus z0 is equal to f partial x at our point times x minus x0 plus f partial y at our point times y minus y0. So if we break this thing down a little bit, it does look quite a bit like the equation for a tangent line, where we just have an x slope and a y slope that are both in there, that x and y slope being the x partial derivative and the y partial derivative. And then it's being multiplied by the difference between x and the point we're starting at for the x partial, and y minus the point we're starting at for the y partial. And then z is the piece that we're setting it equal to. So z0 is sort of like what would have been our just our y point from back in Calc 1 when we did linearization. Also, it's worth pointing out we have the x partial derivative of f and the y partial derivative of f, but we don't have the z partial written down, even though we are kind of using it, since if our surface is z equals f of x and y, then the z partial derivative would be just 1. So really it's all 3 partial derivatives make an appearance here. So if that's our tangent plane, then let's revisit the idea of linearization that we had from back in Calc 1, which linearization basically said that if we wanted to take some complicated function and just make an estimate around some point, we could say that near a point, whatever function I want to use is going to be pretty close to the tangent line at that point. So we'd use the tangent line to create our linearization, basically taking some complicated function and reducing it down to a linear function, hence the name linearization. And in Calc 1, we used a tangent line in order to do that. And we said that our linearization was only really effective as long as I stay pretty close to the point that we started at. In Calc 3, well, now that we have 3-space and a tangent line isn't going to cut it anymore, our linearization is going to have to be a tangent plane instead of a tangent line. So we'll just use the same definition for linearization, but extend it out to a tangent plane. And hopefully you can see that those equations are pretty much the same, where we're just replacing z with L of x and y. So z is that linearization, and then f of x naught y naught is just z naught. Since z is f based on our definition for the surface, we'll just add that one term back over to the other side. And then all the other pieces stay the same. So when we need a linearization, or if we need to compute the error or estimate the error in some term, we'll estimate using linearization, which just means go to a tangent plane. So for our first example, we'll find the equation of the tangent line to the surface. F of xy is 3y squared minus 2x squared plus x at the point 2, -1, -3. So first thing we need if we're going for a tangent plane would be our two partial derivatives. So we'll need a partial derivative with respect to x. And that thing should be 0 minus 4x plus 1. If we just take our derivative with respect to x, then we should also get the value of that partial derivative at the point in question, which is 2, -1. Since I only need the x and y points to get the partial derivative. And if we plug that in, -4 times 2 looks like it's going to be -8 plus 1 is -7. Then we'll repeat that process, but this time for the y partial derivative. Doing so should give us 6y plus 0 plus 0. So then that y partial derivative at our point, which should be 2, -1, plug that in, we'll have 6 times -1, which is -6. And then it's a matter of plugging in all of our points to that tangent plane. So tangent plane should look like z minus z naught is equal to f partial x at the point, but for simplicity's sake, I'm just going to leave it f partial x times, this will be x minus x naught. X minus x naught plus f partial y. And again, this should be at our point, but for simplicity's sake, y minus y naught. So there are all of our pieces, so we just need to plug some things in. So what's this thing look like? We'll have z minus -3, so z plus 3, is equal to f partial x at our point, which is -7. Actually, we're going to have parentheses, so I don't need the parentheses around the -7, times x minus 2 plus f partial y, which is -6, times y minus -1. Ooh, crap. So y plus 1 ends up in there. And that's the equation of our tangent plane, or an equation of our tangent plane. That's probably good enough. We could, solve this thing for z equals a bunch of other stuff, or we could even have it set up so that it's an x, a y, and a z term all added up equals 0. There are lots of different ways you can write down the equation for a tangent plane. This one seems as good as any other, so I'll leave it there. All right, and then let's try some linearization. So we have that R is the total resistance of two resistors connected in parallel with resistances R1 and R2. And if you've seen that equation before, it's the reciprocals all added up is equal to the reciprocal of the total resistance. And we'll say that our two resistors both measure 22 ohms and 43 ohms, with a possible error of 0.5% in each case. We want to estimate the maximum error calculated of R. So what we'll say here is that R should be approximately equal to the linearization of this function at R1 and R2. So R1 and R2 are going to be our two variables. So our big R, the total resistance, again, is approximated by the linearization, but the exact value of R, we're going to say is the function f of R1 and R2. So just to give us a couple of definitions that we can work with. So we can have an exact value for R is the function f, but an estimate for R is the linearization of f at the point R1, R2. So what we're going to want is a linearization about R, which means I need a function or some sort of equation that shows me R equals something in terms of the other two pieces. And at the moment, I have an equation for 1 over R. So the first step is going to be to rearrange that equation a little bit. So right now, I've got 1 over R1 plus 1 over R2. I'm going to change that to look like this. We'll have R2 over R1 times R2 plus that second term, I'm going to rewrite to be R1 over R1 times R2. So notice all I'm doing there is just getting myself a common denominator. The common denominator is going to need to be R1 times R2. So I'm multiplying R2 over R2 into the first term and R1 over R1 into the second term, meaning that I can get the equation, and let's actually write it down here. The equation for R, the total resistance, is equal to the reciprocal of that thing. So I've got R2 plus R1 over R1 times R2. Its reciprocal then it should be R1 times R2 divided by the sum of R1 and R2. R1 plus R2. So now I've got myself an equation for R, so we're going to run with it. So if I scroll down, here I've got the equation for the linearization. Right, so the linearization at a point is equal to the function value at that point plus a partial derivative with respect to the first term plus a partial derivative with respect to the second term. And if we kind of break down what this thing all means, then that first term, it's just f of 22 and 43. So that is the actual resistance if my resistors are 22 ohms and 43 ohms. So this first piece is an exact value. So that is exactly the resistance if there is no error in either of my small resistors. So as long as R1 and R2 have 0 error, then the function value at 22 and 23 is that exact resistance. So this is exact R. Exact resistance, let's just write it all the way out. Which means that all of the other stuff is going to be the error term. So all of the partial derivative stuff, that's where I'm since I'm multiplying it by R1 minus 22 and R2 minus 43, that's just multiplying the distance away from my initial point that I'm starting at. And then we're estimating that error with the derivative piece. So if I want to know the error or estimate the maximum error in the calculated value of R, the thing I really want to be doing is just looking at the error term. So I can ignore that exact value piece and just focus on the error part. So bring that down into that next equation. The error is just the sum of the second two terms. One of those depends on the error in R1, and the second term depends on the error in R2. And let's also just label this guy right here. So this is the error in R, the error in the total resistance. So we'll differentiate that a little bit later on. So if that's my error term, one of the next things I'm going to need will be the partial derivatives with respect to each R1 and R2. So we should go ahead and calculate that. So we've got some, at least for the purposes of finding the partial derivatives, we assume that R1 and R2 are both variables, since they do need to represent variables here. Since R1 and R2 will be the exact value of each of those resistances, as opposed to 22 and 43, which are just the target values for those resistances. That's what we hope they're going to be, but there's some error term, meaning R1 and R2 are slightly different from those numbers. But I digress. Let's calculate this derivative. So it's a quotient, so we need the quotient rule. So if we just remember giraffes forego, that means that G goes first. This is R1 times R plus R2, giraffes. So F is the derivative term, and the derivative of the top with respect to R1 is just R2. It's an X partial, so we're going to color that in purple. So minus the forego part, which means F then G. So minus F, which is R1, R2. So that's 4 times go. The derivative of the bottom is just 1. Since I'm taking a derivative with respect to R1, it'll be 1 plus 0. Then that whole thing gets divided by the denominator squared. So R1 plus R2, that whole piece squared. And if we simplify that thing, we should get R1 times R2 minus R1 times R2 plus R2 squared. So in the end, this thing looks like R2 squared divided by that denominator, which is R1 plus R2 squared. R1 and plus R2. And now, if we were to then do that derivative again, but this time with respect to R2, and since those variables are pretty much swappable, we're going to get the same derivative second time through, just with an R1 squared on top instead of an R2 squared on top. So R1 squared divided by R1 plus R2. Squared. All right, now we have our partial derivative terms. So carry that down. Then the thing that we want next would be to just plug in our derivative values at that point. So we'll plug in 22 and 43 into each of those derivatives, and we'll get those numbers. I'm just going to leave them exact for right now, and we'll come back to them in a moment. And so now we also should deal with the error in each of the two small resistors. So dealing with the error in R1 and the error in R2, and we're going to look at the error two different ways and relate the ideas together. So the first idea is this part right here. We've got R1 minus R2, that's the piece that shows up in the equation. And this thing is just the difference between the exact value and the target value. So the difference between the exact value, which is R1, the exact, we're doing this in gray, the difference between the exact and the target value. And that is that piece right there. Coming at it from the other side, we know that each resistor has a possible error of 0.5%. So possible error of 0.5%. And that's what that second piece is. And if we're looking to estimate the maximum error of the total resistance R, then we want to look at the maximum possible error for each R1 and R2. Which is why we're going to say that if we wanted to maximize the error term of R1 minus 22, then it should be 22 times 0.5%, since that's the maximum error we can get to. If you wanted to, complete that whole equation, R1 is equal to 22 times 1 plus or minus 0.5%, so 1 plus or minus 0.005. And we'll look at just letting both of these things go above their target value. But then if we simplify that thing, that error term just comes out to 22 times 0.005. So I get a maximum possible error of 0.11 in the R1 direction and 0.215 in the R2 direction. Since those same pieces would apply to the R2 calculation, just with a different number plugged in there. It'll be 43 was our target value for R2 instead of 22. So now we've got maximum errors for both R1 and R2. We have an estimate for how the error in R1 and R2 will affect the error of the total resistance R. So the final step is to just put it all together. So the error in our total resistance R is equal to the R1 partial times the error in R1, which is 0.11, plus the R2 partial times the error in R2, which is 0.215. Plug all that into a calculator, and I got 0.727692. And then, round to however many decimal points you need. Our last step should say that this is in ohms, since we were given a unit.